Hi, welcome to this lesson on trigonometry compound angles. So let's have a look at the cosine compound angles. There are a set of important trigonometric identities which we call the compound angle formulae, or otherwise referred to as the sum or difference laws for trigonometric ratios. So let's start off with the cosine compound angle formulae. There are two of them. It states that if A and B are any two angles, then if we take the cos of A plus B or the cos of A minus B, we can simplify them in terms of sine and cosine ratios. So the cos of A plus B is cos sine sine. That's the sort of mnemonic way of remembering it. And then putting the angles as you see them here, A and B. And then there's a opposite sign for cos. So the plus becomes a negative in the middle. And similarly here for cos of A minus B, it becomes cos sine sine. The two angles as you see them, A and B. But instead of minus now, it becomes positive in the middle. Okay, so we're going to prove one of these, and the rest of all the compound formulae that we look at in the future are all going to be derived from this one singular one. So the one that we are going to prove is this one here, the cos of A minus B. And the cos of A plus B, the sine of A plus B, and the sine of A minus B, as we'll see next, all come from this one proof here. So, how does the proof look? Well, first of all, we're going to construct the following diagram in the Cartesian plane. So, from the origin points, we're going to pick 2 points in the plane. We'll call them P and Q, and we'll have the x and y coordinates labeled as follows. For P, we'll call it xb, yb, and for Q, we'll call it xa, ya. Then what we're going to do is drop some perpendicular lines down to the x-axis. So this point D becomes the same x-coordinate, but now it's on the x-axis, so the y value is 0. And the same thing here for C. Now the way we choose these 2 points is quite specific, because we want to choose them such that the distance from the origin to that point is 1 unit in length. Okay, so that's really important that we define it like that. All right. So why have I called P, xb, yb, and Q, xa, ya? Well, those coordinates depend on the angles A and B. So for the point P in space, I took from the origin to the x-axis and I rotated it b degrees. So P was originally lying here somewhere. Okay, but now as I swung it b degrees from the x-axis, I land up here in space. And that point there now becomes P, and that length OP is 1 unit. So it forms a right angle triangle, OCP, with an angle of B here from the positive x-axis. I'll do a similar thing, another point Q, and I would have rotated it A degrees, right, in the general convention anti-clockwise from the positive x-axis. So that is A degrees there, right, and this also forms a right angle triangle, ODQ. Okay, and then lastly, the angle from the blue line to the red line is going to be this total angle A minus the smaller angle B. So that's A minus B degrees. Okay, and then lastly, I'm just going to construct the line between Q and P. So that is the entire crux of the construction part of the proof. So now we're going to do some algebra and analyze. So what the main part of the proof relies on the fact that we're going to calculate the distance PQ in 2 different ways. The first way we're going to do is, or one of the ways we're going to do is the distance formula between 2 points. So that's from your analytical geometry. And then the other way we're going to do it is using the cosine rule. The reason we can do that is because we have the 2 side lengths, 1 and 1, and the included angle between them, A minus B. So we can use the cosine rule. And what we'll find when we're doing the proof is by finding the distance in these 2 different ways and setting them equal to each other, because the distance is the same, either way you calculate it, we will get this desired formula coming out. Okay, so in that diagram, in triangle OPC, so this blue triangle here, we can see that if we take sine of angle B, it's going to be opposite over hypotenuse. The hypotenuse is 1 in length, and the opposite length here is just the y coordinates of P, which is yb. Okay, so that's what we have here. Sine of B is yb over 1, so therefore yb over 1 is just yb, so we get yb equals sine B. Using that same logic, if I do cos B is adjacent, which is the x coordinate, xb, over the hypotenuse, which is 1. So xb over 1 is just xb. So we get the coordinate xb can be written as cos b. We can do exactly the same thing for the red triangle as well, and we'll find that the y coordinate of A is just sine of the angle A, and the x coordinate of A is just cos of the angle A. So we can rewrite the points. Instead of saying xb, yb, we can say that xb is just cos b, and yb is just sine b. Similarly, xa is just cos A, and ya is just sine A. So let's add this information to the diagram. Okay, so now instead of labeling the coordinates like this, xb, yb, I've labeled it cos b, sine b, and the same thing here. Okay, so now that we've got all that information set up, let's calculate the distance in two different ways and go ahead and equate them together. So using the distance formula, right, we see that this PQ length here, so using distance formula, that's PQ squared equals the difference in the x coordinates squared plus the difference in the y coordinate squared. So that's the distance formula, or Pythagorean theorem. So I've got it labeled out here, xa minus xb squared plus ya minus yb squared. Okay, so now I've replaced xa and xb in what we found that they were cos A and cos B, and same thing for ya and yb. Now I square these terms out. So I square the first term, cos squared A, square the second term, cos squared B, and then double the product of the two terms. So there's the product, cos A, cos B, and then doubling it means 2. And because it is minus, it's minus 2. Same thing here. Square the first term, sine squared A. Square the second term, sine squared B. The product is sine A, sine B, doubling it, and then because it's negative, it was negative in the middle. Okay, so now that I've squared out both brackets, I can start to clear up terms. So I'm going to group terms together. I'm going to group the cos squared and the sine squared A together. I'm going to group the cos squared B and sine squared B together. And then what's left over is a minus 2 cos A cos B and a minus 2 sine A sine B, which I've grouped together by taking out a common factor of negative 2. Now sine squared A plus cos squared A, by the square identities for trig, that's 1. And similarly sine squared B plus cos squared B is 1. So this 1 plus 1 gives us 2 minus 2 times this entire expression. So that is PQ squared simplified using distance formula. Now, if we use the cosine rule, so again, let's just remember, so this was Q and this was P. The angle between here was A minus B, and the side length units were 1 and 1. So, from the cosine rule, this side squared is equal to this side squared plus this side squared minus 2 times the product of these two sides times cos of the angle in between them. That is the cosine rule. So I get 1 squared plus 1 squared minus 2 times 1 times 1 times cos of A minus B. Simplifying that, I get 2 minus 2 times cos A minus B. So PQ squared is equal to PQ squared. That's what we said. The distances are the same, right? So now I can say from the distance formula, that's what I worked out. And from the cosine rule, that's what I worked out. Now I can subtract 2 on both sides, and I'm left with this negative 2 times that equals negative 2 times that. Then I can divide both sides by negative 2, and what are we left with? Cos of A minus B equals cos A cos B plus sine A sine B. That's exactly the formula we wanted to show. So we've successfully mathematically proven that cos of A minus B equals cos cos sine sine, where you put A and B, and the sign in the middle is positive, opposite of the negative sign. Now we can use this to show that cos of A plus B is the same thing, cos cos sine sine, AB, but now the middle sign changes. So I'm going to write cos of A plus B in a specific way. I'm going to write it as cos of A minus B, because if you distribute that out, you get A plus B. Now we know what cos of something minus something is. We just worked it out. It's cos cos sine sine, the angle as you see it, so A and negative B, because that's the angle we're looking at, negative B. And then it's a plus sign in the middle, because there was a negative there. Now, cos of negative B is cos of B from this identity here, the even trig identity for cos. And the sign of negative B is the negative sign of B, and that is because of the odd trig identity for sine. So simplifying, this cos negative B becomes cos B, and the sign of negative B becomes negative sine B. So cleaning all this up, we have cos A times cos B. Now, this negative sign, right, if you're multiplying a positive by negative, it becomes negative. So it's negative sine A times sine B. So we've proven that cos of A plus B is cos A cos B minus sine A sine B. Okay, so these are the compound angles for cosine. We'll have a look at the compound angles for sine and then do some questions with these. All right, I'll see you in the next one.